Okay, so hello and welcome everyone to week 12 of interactive live sessions for the course on Computational Fluid Dynamics for Incompressible Flows. So as you all know, this course is being offered by NPTEL. It's being instructed by Professor Amaresh Dalal from the Department of Mechanical Engineering at IIT Guwahati. My name is Debjit. I'm a PhD scholar at IIT Madras, and like every other week, we shall be solving some problems together and having discussions regarding anything and everything related to the course. Now, this is officially the last day, but not actually, because uh, coming tomorrow on 17th April from 6 to 7, we will have a revision session. Okay, so try to attend that as well. It would cover all the topics covered over the full course, as opposed to today, which deals with only the lectures of week 12, in which we learned about simple algorithm and associated uh, stuff. So without any further ado, let's get started. So this is the first question of today's session, which is asking us that for solving the Navier-Stokes equations using finite volume method, abbreviated as FVM, what are the disadvantages of using a collocated grid? We have been looking at collocated grids and staggered grids for quite a while now. In reference to solving Navier-Stokes using finite volume method, what are the specific disadvantages of it? Is it option A, that pressure difference between alternate grid points are taken? Is it option B, velocity of the cell center does not appear in the continuity equation? Is it option C, that wavy velocity or pressure fields are treated as constant fields? Or is it option D, all of the above? That is, all A, B, C are disadvantages of using a collocated grid. So read the question and all the options carefully. Then once you have figured out the correct solution, you can either type it in the chat box or you can unmute and answer as well. So FVM is basically finite volume method. So over this course, we learned primarily finite difference method, which covered the initial 9 or 10 lectures of the course. Then we shifted gears and moved on to finite volume method. There is also finite element method, which can be used for solving fluid dynamics problems, but that is not within the purview of this course. Maybe you can look at some other course if you are interested in learning that. Okay, so back to question number 1, which is asking us that for solving Navier-Stokes equations using finite volume method, what are the disadvantages of using a collocated grid? Is it option A, pressure difference between alternate grid points are taken? Is it option B, velocity of the cell center does not appear in the continuity equation, which someone has answered? Or is it option C, that wavy velocity or pressure fields are treated as constant fields? Or is it option D, all of the above? We have one response so far in favor of option B. Let's hear what others have to say. Okay, so let's have a look at the solution. It's actually option D, all of the above, because all of these are true. So the first point, we'll go through each of them. So the first point says pressure difference between alternate grid points are taken. So basically, if you are trying to find out the pressure difference across this cell, so dou P, dou X at point P, if you're trying to find out, then it essentially you will have to take uh, PE minus PW by 2 delta x, if delta x is the size of the grid points. So essentially we are losing resolution over here. So I had taken points delta x apart, but I have to consider those points which are 2 delta x apart. So whatever mesh I am taking, it's not being fully useful. Only half of it is being useful. So therefore, option A is correct. Then option B, the velocity of the cell center does not appear in the continuity equation. This is also correct. So if we are trying to satisfy the continuity equation at a certain cell, then all the velocities at the adjacent grid points appear. So basically, if this is P and this is E, east, west, north, south. So basically, the continuity equation ends up looking like this: UE minus UW into delta Y, which is the uh, area through which it flows, and plus Vn minus Vs into delta X equal to 0. So this is the continuity equation in the integrated form. So here also UP or UV or VP does not appear. So this is also a disadvantage, because if you're trying to solve the continuity at some cell, at least the velocities in that cell should appear, right? You're only dealing with the neighboring points. What use is that? So this is also another disadvantage. Then of course, this is same as finite difference method as well, that if wavy velocity or pressure fields are used, they basically appear as constant fields. So for this, we can go back to here, an example here. So let's say uh, the pressures at my points over here are something like 200, 0, 200, 0, 200, like this, a zigzag sort of a pressure field, a wavy pressure field. And then essentially, if I'm trying to find out dou P dou X, which is PE minus PW, this will be 200 minus 200. So the pressure gradient would be 0, which is again not true. There is a wavy pressure gradient as well. And this same thing happens for wavy velocity fields as well. They basically appear as constant velocity fields because essentially my resolution is half because of using a collocated grid. So all these three are disadvantages of using collocated grids. So that's why if you had to pick the correct option, you had to pick option D, that is all of the above. Any questions on this? Okay, so if not, we will keep moving along. We'll move on to question number 2 now, which is asking us, for solving Navier-Stokes equations using finite volume method, what are the advantages of using a staggered grid? Now we look at the other side of the coin. We looked at disadvantages of a collocated grid. Now we will look at the advantages of a staggered grid. So option A says the pressure differences between adjacent grid points become natural driving force for velocity components. Option B says that the differences of adjacent velocity components appear in the continuity equation. Option C says all of the above. So C being all of the above means A and B. Or is it option D, that is none of the above? That is neither A nor B and obviously not C are correct. So once again, read the question and the options carefully. And once you have figured out the solution, you can respond in the chat box or you can unmute and answer as well. So we have a quick response in favor of option C, telling that it's all of the above, basically meaning both A and B. Let's hear what others have to say. Pressure differences between adjacent grid points become natural driving force for velocity components. Differences of adjacent velocity components appear in the continuity equation. Or is it option C, all of the above? Okay, so let's have a look at the solution. It is option C, all of the above. So basically both A and B are correct. So let's quickly go through this. So let's say I have a staggered grid which looks something like this. So this is my pressure cell P, then I have a staggered grid like this, at the center of which U is saved. So this is U small e, this is capital E. Then I have another grid like this, at the face of which V is stored, so Vn. Similarly, I have a Vs over here and a UW over here as well. This being capital W, this being capital N, this being capital S. Right? These are the neighboring cells. The first point, that pressure differences between adjacent grid points become natural driving force for velocity components. So let's focus on this one. So we will just focus on this U cell, right? So in between I have U small e, I have a pressure here at capital E, I have a pressure here at capital P. So you can see that within this control volume, it is the difference between the pressures on two faces of the control volume that becomes a driving force for this velocity UE. And the same thing goes for the vertical velocity here as well. So I have PP here and a PN here and a VN, V small n over here, where the pressure difference between the top and bottom surfaces of this control volume becomes a natural driving force for the velocity in between. So that's why option 1 is correct. And the second one, the differences between adjacent velocity components appear in the continuity equation as well. So for that we have to consider our central control volume, that is capital P. So here I have here I have UW, UE, Vn and Vs. So all the velocity components at the surfaces of that particular control volume are being conserved. So here the continuity equation would look like something like this. This into delta y plus Vn minus V small s into delta x being equal to 0. This makes more physical sense, right? So here is a control volume and all the velocity fluxes coming in are the ones going out. So that's how the continuity equation is satisfied. So option B is also correct, and that's why the correct answer should be option C, that is all of the above, both A and B, and option D would be incorrect, none of the above. Right? Any questions on this? So these were the advantages of using a staggered grid. All right. Okay, so let's move along. We'll move on to question number 3 now. Okay, so this is a very simple question. What is simple method in CFD? What is the full form of this abbreviation which we use? Simple, SIMPLE. Is it option A, semi-implicit method for pressure-linked equations? Is it option B, spectral implicit method for pressure-linked equations? Is it option B, simplex method for pressure-linked equations? Or is it option D, spectral implicit method for partial differential equations? Okay, so we have a few responses in favor of option A, semi-implicit method for pressure-linked equations. Let's hear what others have to say. Okay, so let's have a look at the solution. It is actually option A. This was a easy one, so you simply had to know what it is. You can't really figure it out if you don't know. So it's the semi-implicit method for pressure-linked equations, SIMPLE. So why pressure linked equations? Because Navier-Stokes equations have this unique term called uh, grad of P which appears. So this is pressure linked equation, and semi-implicit method because so the original equations, they turn out to be implicit equations where AP UP equal to some summation of A N B U N B plus some source term B, right? Here what happens, and I'm not writing the pressure term over here, so the pressure term is also within the source term, so there will be another term containing pressure uh, the pressure differences. But anyway, so here in this method, what is done is this implicit equation is made forcefully made into a semi-implicit method by taking this term to be zero. I'm sorry, so these are all corrections basically. So this is made to be zero. So that's how an implicit method is made into a semi-implicit method, and the original equations which we are trying to solve are pressure linked equations. So that's how this method gets its name. It's widely used in CFD, and this method was originally coined by an Indian engineer and researcher known as S.V. Patankar. He has a book written on finite volume methods as well, so it's a very good book, and you can always go through it if you want. Dr. S.V. Patankar. Okay, so I hope things are clear. If not, you can always stop me and ask. Okay, all right, so we'll keep moving. We'll move on to question number 4 now, which is asking us what is the difference between the simple and the simple R method? Is it option A, that simple R uses an additional velocity correction equation? Is it option B, simple uses an additional velocity correction equation? Is it option C, simpler is a fully explicit method? Is it option D, simple is a fully implicit method? Which one should it be? Options A, B, C, or D? So simple R is basically simple. It's the same abbreviation as our earlier, simple revised. That's how it gets its R from. Is it option A, that simple R or simpler uses an additional velocity correction equation? Is it option B, simple uses an additional velocity correction equation, which we just now received a response in favor of? Is it option C, simpler is a fully explicit method? Or is it option D, simple is a fully implicit method? We have one response so far. Let's hear from the others. Which one should it be? Okay, so let's have a look at the solution. It is actually option A. Simpler uses an additional velocity correction equation. So what is done in simpler is basically uh, so initially so in simple what is done is basically an initial guess pressure field is assumed, and then we get the pressure correction equation, and then we correct that, and the velocity corrections are related to that pressure correction, and then that is solved in an iterative manner. What happens in simpler is that we do not guess the pressure field. We start with a guess velocity field, then from this we try to estimate the pressure field. So there is a calculation over here which gives me the pressure field. Then we use it to find out a pressure correction, but we do not correct the pressure. We simply use it to find the velocity corrections and then add them to the guess velocity field. So these are added, and then again this loop goes on. So this additional velocity correction equation is solved in simpler. Does that make sense? Any questions on this? Okay, so I have a question in the chat box. Sir, is this possible to get this video today? Yeah, I'll try to upload this today itself. Any more questions? Anyone? All right, so if not, we will keep moving on. We move on to question number 5 now, which is now asking us what is the main advantage of using the simplex or simple C algorithm over the simple algorithm. So once again, we have another modification of the simple algorithm known as simple C, or C stands for corrected. So what is the main advantage of it over the simple algorithm? Is it option A, that it can handle compressible flows? Is it option B, that it does not require under relaxation? Is it option C, that it is computationally more efficient? Or is it option D, that it is better suited for unstructured grids? Okay, we have one response in favor of option C, that it is more computationally efficient. Let's hear from others. What is the main advantage of simplex over simple? Is it option A, B, C, or D? We have one response so far in favor of option C. Okay, so let's have a look at the solution. It says it's option B, that it does not require under relaxation. So this is the main advantage. Also, I'd like to say that option C is also not incorrect. This is also correct, because simplex does turn out to be more computationally efficient as compared to simple. So both B and C should have been the correct answers. So first of all, in simple algorithm, what is done is the uh, the corrections at the neighboring points are the velocity corrections at the neighboring points are completely ignored in the simple algorithm. So that may lead to divergence of the pressure correction equation. The pressure correction equation might diverge in case of simple algorithm. In order to not allow that, one of the simple fixes which is put in is simply uh, while adding the correction, a smaller number, a number smaller than 1 is put in. So alpha is the under relaxation factor, which is usually kept between zero point 0.6 and zero point 0.8. So this slows down the convergence while preventing divergence. So this is a simple, I shouldn't say simple. So this is uh, one smart way of tackling this issue. Uh, Whereas in case of simple C algorithm, there the neighboring terms are not ignored. So what happens is simply this. So basically, my velocity correction equation looks something like this, right? So this equal to summation a n b u n b prime plus b. So in simple algorithm, this is totally ignored. Whereas in simplex algorithm, this is so estimated as UNB primes are all equal to UP prime. So that actually simplifies this equation down to AP UP prime equal to UP prime into summation of A and B plus B. So then you can take UP prime on the other side and find out the velocity correction equation. And these B's have the pressure corrections within them. So essentially you avoid the chance of divergence altogether in the simplex algorithm by not ignoring the neighboring correction terms, and it makes it more computationally efficient as well. So it's a better algorithm than the simple. So both the simple R and simple C are improvements over the simple algorithm. And one advantage of simple C over simple R over simple R is that there is no additional equation which has to be solved. In simple R, we saw that we had to solve an additional equation in the algorithm for it to work. So in simple C, that is also not required. So simple C is overall more advantageous among the three methods. Okay, any questions on this? Okay, so if not, we will keep moving along, which is now asking us what is the purpose of the pressure correction equation in the simple algorithm? Is it to correct the velocity field for the pressure gradient? Is it to correct the pressure field for the velocity divergence? Is it to correct the turbulence model for the pressure gradient? Or is it to correct the mesh for the pressure gradient? Very simple question, what is it? I'm expecting a lot of responses for this one. Read the question carefully as well as the options, and then you can put in your response in the chat box, or you can unmute and answer as well. If any part of the question is unclear, then please do not hesitate to ask as well. Okay, we have one response in favor of option B. Let's hear what others have to say. To correct the pressure field for the velocity divergence. Okay, so let's have a look at the solution. It is actually option B, to correct the pressure field for the velocity divergence. So the divergence of velocity, once you integrate it over the control volume, this basically boils down to summation of UFAF, which basically, and if you multiply rho with it, then this basically becomes the summation of f ff is equal to 0. So this is the where f is basically rho u a at different surfaces. So ff is rho u f a f basically. So for four faces there will be four different f's. These are basically fluxes, the mass fluxes, and the summation of the mass flux is equal to 0. This is what the continuity equation also says. So this velocity divergence is what is uh, basically the convergence of this term to 0 is what we check. And for doing that, we need to correct the pressure. We start off with a guess P. We find out what the pressure correction P prime is, and then we add it to this. And then we check if this velocity divergence has become 0 or not. If it has become 0, then we break out of this loop. Otherwise, we keep on correcting this, and this loop goes on and on and on until the convergence is achieved. So that is the main crux of the simple algorithm. And that is the main purpose of the pressure correction equation as well. It is to correct the pressure field for the velocity divergence. Am I able to make things clear? Any questions so far? Okay, so if there are no questions, I'll assume everything is pretty clear and we will keep moving on. We'll move on to question number 7 now. This is a very easy true and false type of question, which is asking us that in the simple R algorithm, the pressure correction is performed after solving the pressure correction equation. Is it true or false? Is it option A true or is it option B false? You can type in the chat box or you can unmute and answer as well, however you feel comfortable. Come on, what would it be? If all the previous questions were simple, then this question is simpler, even simpler. Okay, we have a response in favor of option B, false. Let's have a look at the solution. It is actually false. So the pressure correction is not performed at all in the simpler algorithm, as we discussed earlier as well. So we find the pressure correction, then we use it to find the velocity corrections, and then we plug that in to find the uh, new pressure field. we do not add it. We don't do this step as we do in the simple or the simplex algorithm. So the pressure correction is never performed in simpler algorithm. Okay. Any questions on this? All right. So we'll quickly move along to question number 8 now. In finite volume method, if velocity at the boundary is known, how is the boundary condition handled? Is it by taking option A, the pressure gradient is set to 0, or is it option B, pressure correction gradient is set to 0? So mathematically this would mean dou P, dou N. N can be X or Y depending on the boundary, this being 0, or is it the pressure correction gradient dou P prime dou N equal to 0? If given the condition is that if the velocity at the boundary is known. So let's say VB is some known quantity. It can be a constant, it can be a function with respect to X or Y or even T, but whatever, it is a Dirichlet type boundary condition where velocity is given. How would we handle it in finite volume method when we are using something like simple, simpler, or simplex? Okay, so let's have a look at the solution. It is actually option B. The velocity correction gradient is set to 0. So basically what it means is something like this. So let's say this is my cell and this is my boundary. So, and the velocity over here. So let's say some UB that is known to me. Then what I'll do is that, let's say this is PP and there is some fictitious cell over here. I'll call this PB maybe. So here UB is known, UB is known, but that doesn't mean that PP or yeah, so that doesn't mean PP minus PB by some delta X will be 0. No, this can be some positive value, right? More important, not positive, any finite value. In fact, if it's not finite, then this won't drive the velocity in the first place. But if I already know the velocity, then I know that the velocity correction will be 0. And that would mean that the pressure correction terms, they would be, the gradient of that would be 0. So it's the pressure correction gradient that is set to 0 if the velocity at the boundary is known. Because we don't need to correct it. We already know what it is and it is 0. There could be some corrections inside the domain, which is again added to the guess pressure values, and we subsequently uh, converge, and then our pressure corrections would also become 0. But at the boundary faces where the velocity is known, then the pressure correction gradient will also be 0. Does that make sense? Any questions, anyone? Okay, so if there are no questions, we'll keep moving on. We'll move on to question number 9 now. Okay, so here you'll need to do some work. So there are 4 steps given here, capital A, B, C, and D. You will have to arrange them in the correct sequence of steps. Yes. Any questions?
No, sir.
Okay.
Sir, is this possible to get this video today?
Yes, I said so. You asked in the chat box, right? I hope
Yes,
I
yes, yes.
responded earlier. That
Yes, yes, yes.
I will try to upload this video today itself.
Sure, sir. Thank you, sir. Thank you, sir.
Okay. So what would be the correct sequence of steps in the simple algorithm? Is it option A? Sorry, step A. So there are 4 steps given here. You will have to arrange them in the correct order. So the first one is option A, check for convergence. Option B, solve the pressure correction equation. Option C, solve for the velocity field using the guessed pressure field. And step D would be to update the velocity and pressure fields using the corrections. So it could be a mix and match of all these steps. What is the correct order? Is it option A, B, C, D, A? Is it option B, C, B, A, D? Is it option C, C, B, D, A? Or is it option D, A, D, C, B? Take your time, but find out the correct order and let me know in the chat box. Okay, we already have a quick response in favor of option C, telling that it should be CBDA. Let's hear from the others. What is the correct sequence of steps in this simple algorithm? Step A, check for convergence. Step B, solve the pressure correction equation. Step C, solve for the velocity field using the guessed pressure field. Step D, update the velocity and pressure fields using the corrections. And the 4 possible sequences are option A, B, C, D, A. Option B, C, B, A, D. Option C, C, B, D, A. Or is it option D, A, D, C, B? Let's have a look at the solution. It is actually option C, so correct, whoever chose it. So basically what we do is we start with a guessed pressure field, then we solve for the velocity field using it. So that would be step C. Then using these, we find out uh, the we solve the pressure correction equation, and then we find out the velocity corrections as well, and then we add them to the previously guessed values. So that would be, so no, sorry. So this itself, solving the pressure correction equation, would be step B, and the associated step is calculating the velocity corrections as well. Then what we do is we update the guessed field. So P star plus P prime, U star plus U prime, V star plus V prime. We make these corrections, or we make these updations. So that would be step D. And then we check for convergence, whether our pressure fluxes add up to 0 or not. Right. So this would be step A. And if it is converged, then we stop here. Otherwise, we again go back to the first step and we keep going on. So not the first step, we will just replace P star with P star plus P prime, and then follow the same steps same sequence of steps once again. So that's why C, B, D, A would be the correct sequence. Yes, any
Uh,
questions?
Sir, can you explain once again?
Okay. So we first of all start with the guessed pressure field. Then we find out the uh, velocities using that guessed pressure fields. So these are not correct velocities, right? So then we use the pressure correction equation to solve for the pressure correction P prime, and there are relations of velocity corrections U prime V prime as a function of this P prime. So using this P prime, we can find out this U prime and V prime. Then we add all these corrections to the previously guessed values. So P star, U star, V star, we add our corrections P prime, U prime, and V prime to them. Then using these velocities, the updated velocities, we find out what the fluxes are, and then we check whether they satisfy the convergence criteria or not. So if it's so usually it doesn't become 0, it becomes a very small number. We can take 10 power minus 6 or whatever. Some we will set some tolerance for it, some epsilon, and if it is smaller than that, then we will break off the convergence over there, and we will tell that this is the solution which we have found. And if not, then we will again go back and use our updated values as the new guess values, and then follow the same steps once again. Does that help? Does that clear things up?
Yes, sir. Yes, sir.
Okay.
Thank you, sir.
Okay, thank you. Any more questions, anyone? Okay, so if not, we will move on to the last question of today's session, which is question 10. It's a similar question once again, but this is now asking the correct sequence of steps for the simpler algorithm, simple R algorithm. So here the steps are: step A, solve the pressure correction equation; step B, calculate FF hat and solve the pressure equation; step C, solve for U star V star and calculate FF star; and step D, update the velocity field using the velocity corrections but not pressure. Once again, we have some possible combinations here. So option A, BCAD; option B, CBAD; option C, CBDA; and option D, ADCB. So take your time, read these steps correctly and arrange them in the correct order. It is similar to the previous question, but here the algorithm is different and the steps are also different. So you'll have to read through them carefully. All right, so let's have a look at the solution. It is actually option A, BCAD. We will see why. So in the simpler algorithm, the initial pressure field is not guessed. Okay, so we just start off with U star and V star, and that gives us some U hat and V hat. Look at the details in the lectures. So these are basically some U star minus U star P minus UNB, sorry, ANB star minus B divided by something. Actually, no, this won't be here. If we start something like this. So anyway, so we find out these hat values and then we use them to find out FF hat. So that would be our step B. And using this FF hat, we solve the pressure equation. P star is some function of FF hat. So this is step B, which is our first step. Then we solve for U star and V star. So basically, once we have found out the P star, then that gives us a new set of U star and V star. This is the additional pressure equation which we spoke about earlier. So this is step C. Then what we do is we solve the pressure correction equation to find out the pressure corrections, but we do not add this to the guessed value of P star. We simply use it to find out the velocity corrections, which are then added to the velocities. This would be step A. Solve the pressure correction equation. Okay, so this next part would be option D. So this part won't be here. So, once you have found out the pressure correction, we can find out the velocity corrections, which are functions of this pressure correction. Then we simply add them to the velocity field, which we already have. And then we check for convergence. If it's not converged, we will again go back. So the correct sequence would be BCAD. Any questions on this?
So not very clear. This
Okay,
simpler.
so let's go through this again.
Physically unable to understand this.
Physically,
Mhm.
yeah, that's difficult because we are talking about
Physical in the sense
numerical algorithms here. But
sequencing is not very clear.
okay, so basically in simpler, we do not assume any pressure, we do not correct the pressure as well. We assume velocity field and calculate the pressure, and there is a pressure correction equation which is solved, but that somehow does not, the pressure correction is not added to the pressure. We simply use that correction to find out velocity corrections, and then again we use that correction to calculate the pressure again. So if you look at steps C to D, it becomes clear. So P star, I have this as a function of some U star V star, right? So after I know U star V star, I can calculate P star. And there is a pressure correction equation which is solved. Then using this, I can find out velocity corrections which are then added to these U star and V star, right? Then again, these are used to calculate the P star. So this is the sequence. But never P star is not corrected as P star plus P prime. No, this is not done. And this is the prime difference between simple and simpler algorithm. This equation does not exist in the simple method, but in simpler method it does.
So, sir, by virtue of guessing the velocity field, what is the advantage vis-a-vis the simple method?
Uh, Advantage is that so in this equation we do not ignore this term. In simpler in general simple method, this is usually ignored, so that results in the chance of the pressure equation getting diverged. This again, divergence is not possible because these terms are not ignored, they are kept as it is, so it's a bit more accurate as well. So this method makes less number of assumptions than the simple method.
Right, sir. Right, sir.
Okay. Any other questions, anyone? Otherwise, we have come to the end of today's session. So thank you. Hello.
Tomorrow 5 p.m. class.
No, 6 p.m.
Tomorrow is 5 p.m. sir.
No, tomorrow 6 p.m. Just the usual timing.
One message came 5 p.m. Okay, okay,
Okay.
okay, sir. Thank you, sir. Thank you.
Okay. Thank you. Bye. Good night.
Thank you, sir.
Thank you.
Good night, sir.
Yeah. Bye.
Thank you, sir.